This part of the lesson, we'll learn the confidence interval for proportions. Proportion comes up when we have the different categories, and we are interested in estimating the proportion of one category. Generally, we could formulate this kind of problem as in Bernoulli random variable. We learned the Bernoulli and the binomial distribution in the chapter 5. Here we will, this slide will briefly go over the binomial proportion. When we have data that are binary, we can denote each of the value as 0 or 1, and the probability of 0 is given by a probability that say the probability of 1. Probability of 1 is given by P. And this P, when we calculate the expected value, it's also equal to the expected value of the random variable. So basically, P, this proportion of ones, is also the on average what proportion of the ones that you will see in a long-term experiment, many of the repeated experiment many times. The standard deviation for the Bernoulli random variable is equal to the success probability times the failure probability taking square root. So square root of P times 1 minus P. When we consider the total number of ones in the Bernoulli trials, what we get is actually becoming the binomial random variable. So this Sn is the sum of these xi's. Imagine each of the xi is either 1 or 0. And when you consider the sum of that, you are basically counting how many of them are of that same category, or how many of them are in the success category. And x bar is adding up all of the values in the xi and divided by n. So if you think about it, some of them are 1, some of them are 0, eventually after you divide it by n, what you get is a proportion of the ones. So that's the meaning of this x bar sample proportion and the sum total. So this word, this phrase, sample proportion, I will use it frequently from now on. Whenever I call sample proportion, I simply mean it's the average of these observed Bernoulli random variables. Sample proportion. The observed sample proportion is an estimate of the population proportion. You know, this population proportion is something unknown, but we would like to know what is the value of that. And sometimes we make statement about this population proportion. We need to use the data to try to help to decide whether the statement is plausible or not. The sample proportion, this x bar, has the same center expected value as the population proportion. So if you try to calculate the expected value of sample proportion, you'll see it's equal to the population one. And if we calculate the standard deviation of x bar, as we learned in the earlier chapters, we know it's equal to the variance of xi divided by the n and then take the square root. Variance of xi is simply equal to p times 1 minus p, and after we divide by n take square root, this gives us the standard deviation of sample proportion. The n is inside of the square root. These two things, you will need to remember it because we will use them frequently regardless of in the lecture or in the homework assignment. So both of these, the mean and the standard deviations, need to be memorized. So in many of the questions, it involves estimating a proportion, and we are going to use the sample proportion x bar to start the process. Sample proportion quite often is also denoted as p hat. So the p is population proportion, and then p hat is the sample proportion. It's just a different notation, but still represent the same average from observed sample. Okay. Once we have the sample proportion, the next is to consider how to estimate the population proportion with an interval. Recall back then when we consider just one sample mean, when we try to consider confidence interval, we will end up having the X bar plus minus the Z times standard error. In this case, it's similar because this sample mean still is approximately having normal distribution, but the problem will require us to estimate the unknown standard deviation, sigma. And here the sigma, we know is square root of the p times 1 minus p, but the p is unknown. So we also need to come up with something to put in there to give us a estimate of the sigma. In the data, when we have the data, like the continuous data, we were able to use the sample standard deviation to estimate it. But in the Bernoulli binary data, we already know that the variance is p times 1 minus p, so we can use this p hat times 1 minus p hat to give us the estimate of the variance. Therefore, standard error of X bar will be estimated by the p hat times 1 minus p hat, and then divide by n, take the square root. This is the estimate of the standard error. So estimated standard error, not the standard error. Standard error itself refers to the p times 1 minus p over n. Okay, so that's the estimated standard error. And then when we have n being large enough, then we can use this population we can use this confidence interval formula. So this part, the p hat is basically the X bar, and here's the percentile from normal distribution, and then the standard error of X bar. And in this case, since we replace the population standard error of X bar by the estimated standard error, we will have p hat plus minus the Z times the square root. And under the square root, we have this p hat and 1 minus p hat, and need a parenthesis to be closed, and then divide by n. So this is a large sample confidence interval for the p. So keep in mind, this is for the large sample, okay, large n case. How large in this case do we need? That kind of depends on the p. If the p is pretty small, for example, close to 0, or if p is very large, close to 1, because p is always between 0 to 1. So if p is either on the 0 side or on the 1 side, in either case, the variation will become close to 0, and this estimate is no longer actually good. So even though you're thinking of using the normal approximation, but we have seen in chapter 5 that the normal approximation requires a very large n in order to be not skewed. So generally, how large do we want to use this formula? 1,000 is a good number to consider. When it's more than 1,000, we could use this one. But if it's less than that, sometimes people could use a adjusted formula rather than this one. So that adjusted formula would involve this p hat, and also beyond that, also involve additional calculations in there. Both the adjustment will be adjusting the p hat and also adjusting the estimate of the standard error. The textbook, the Walsh textbook, did give a formula with that adjusted one. Here, I'm going to skip that because that formula is it's pretty simple. I mean, in terms of the formula itself, writing is messy, but the idea is simple like this one. Simply, you use the estimate and then plus minus the Z, the normal percentile, and then times the standard error estimate. Okay, so this is the confidence interval. Here's an example about it. We're looking at the feasibility of offering new service in a large Midwestern city. In order to propose a new service to be economically viable, it's necessary to have at least 50% of the customers willing to add the new service. So they did a survey, and out of 1,218 customers, 516 of them said they would add the new service. So based on this number, do you think that the company should expand the capital to offer the new service in the city? So when we look at this number, 516, and this is 1218, by directly comparing the numbers, then this number is less than the half of the customers. But as we know, these sample proportions are just averages from the collected sample. It's likely that they change from one sample to another sample. So we cannot just simply make conclusion without trying to check carefully about the probability of the probability of this estimate to be below the 50%. So we'll try to consider a confidence interval to an interval estimate of the mean proportion of customers that will add the new service. So here, our p hat is 516 divided by 1218, and then we want the population proportion, and we use the estimated standard error and estimated sample proportion to give us confidence interval. So with n equals 1,218, we use this normal approximation to the distribution. So p hat is approximately normal, which comes from central limit theorem. Remember, p hat is simply just the sample mean of those 0 ones. Okay. And the standard error here is estimated with the p hat and 1 minus p hat divided by the n. And now we're ready for the confidence interval. We put in the n and the p hat and also the alpha. Alpha is always 1 minus the confidence level. Then we use the Q norm with the two of these proportions, and then we put the p hat, which is the center of the interval. And then we have the square root of p hat times 1 minus p hat and divided by n. Then what we have is the confidence interval. The result of the confidence interval, if you look at the numbers, 0.395 and 0.45, clearly that 0.5 is not in the interval. So this procedure that we're trying to construct the interval is like, this is one of those like 95% of the time the interval should contain the true mean. And this one does not contain the 0.5. Therefore, we are basically 95% confident that the proportion of customers that want to add the service is less than 0.5. If that's the case, then the company should not expand the capital to offer the new service. So we use this confidence interval compared to the targeted value 0.5, see whether this targeted value is inside of the interval or not to make the judgment. Another example here, we take a simple random sample of 900 voters, and we find that 486 are in favor of a candidate, a particular candidate. What do we know about the true proportion of P in support of that candidate? Is this candidate likely to win? Let's suppose we have only, okay, we don't really need to worry about how many candidates. As long as this candidate has more than half of the proportion of candidates that support this candidate, then this one will win. So basically, it's a question of 486. Is that going to tell us that if we consider the bigger population, the entire population, are we going to have more than 50% of voters in favor of this candidate? So let's first compute the estimate. P hat is the sample proportion 486 divided by the 900, and that gives us 0.54. then what we just need to make sure is if we consider the 1.96 standard deviations below this p hat and 1.96 standard deviation above that, whether that's going to be going, entire interval is about 0.5 or not. So the standard error in this case, we use the p hat and 1 minus p hat and divide by n, take the square root. Again, this one is a little bit, the sample size of 900 might be, if you think about what we say for the large n, this n 900, generally we would hope to use more than 1,000 to use this formula when n is more than 1,000. But in this case, it's not a concern. That's because the p hat is 0.54. And when the sample proportion is close to 0.5, we know that the distribution is pretty symmetric. Therefore, it does not need a very large n in order for this normal approximation to work well. So in this case, we'll proceed with the large sample confidence interval. So we have this 95% interval is the p hat plus minus 1.96 and the standard error there. After finish computing, we see the interval is 0.507 and 0.573. The entire interval is above 0.5, so we can say that the candidate is likely to win. With 95% confident that this candidate is likely to win. This computation, we have done it manually. We don't have to do that manually. If you do it in R, we use the qnorm command and you put in the 2 percentiles. This is the 2.5 percentile, 2.5, and the other one is 97.5%. But we always have to use it as proportion here. And the center for the confidence interval is 0.54. So we put this mean 0.54 and standard deviation 0.0166 there. So that gives us the confidence interval. Okay, so that's the example 6. So for this example, however, p hat is close to 0.5, so we didn't need n to be too large for the central limit theorem to be applied and stay valid. So what are these confidence intervals good for? Basically, the confidence, when we do a point estimate, we're just thinking about one single X bar. And now when we do the confidence interval, we're basically taking into account the standard deviation of the X bar. So that helps us to consider how much this X bar actually varied compared to the center mu. If what we get is after we take into account of the variation, we're able to find that the mu is in the interval, then that gives us a pretty good assurance if confidence level is high. On the other hand, if our interval, after taking this interval already taking into account of the variation, and if that interval does not contain the mu, then we basically are also confident that the mu is not equal to that, is not of a specified value. Okay, so that's this confidence interval. You can use this confidence interval to check whether a hypothesized value mu0 is reasonable or not by checking whether that value is in the interval or not. So we learned how to compute the confidence interval. This next part is to try to consider further about the interval to see what affects the width of the interval. Sometimes after you have computed the interval, you might think that the interval is too wide. In that case, how can we make it shorter or narrower? The interval is always centered at X bar. So if you look at it, we suppose if you have different computations, and as long as you have these averages to be the same, it's always centered at this X bar. So here, this part I'm sorry, I should not be touching that one. So instead, when we consider the interval, here is the center, which is the x bar, and on the left-hand side, we'll have all this move to the left a certain amount and move to the right a certain amount. How much do we move to the left and how much to the right? This is simply the z, this is the percentile, and then the standard deviation over square root of n. Since here is always the center, okay, center is always staying as the average. And then if we want to make it narrower, we would need to shrink this part, right? This is the part that we need to shrink in order to make the interval to be shorter. And to shrink that, you see this term involves three quantities: the percentile z, the standard deviation, and the square root of n. The percentile, this percentile definitely changes. Like for example, if we look at the table here, when the confidence level is 0.9, in that case, this alpha over 2 is 5%. And then when we consider the z value, in this case, it's the 95 percentile. This one, 95 percentile, 1.645. So that's 95th percentile. And if we consider 0.95 as the 95% confidence interval, in that case, we will need 97.5 percentile because we want both sides to be. So if in the middle we want 95%, then this right-hand side needs to be 2.5%, and the lower is also 2.5%. Total give us the 100%. And if we have 2.5% on the right-hand side, then this upper, this one is the 97.5 percentile. And 97.5 percentile is 1.96. That's the value, 1.96. So as we increase this confidence level, as you see, it becomes larger and larger for this percentile, the normal percentile. So maybe you might be prompted to think that if I want the interval to be narrower, I could just reduce this confidence level. Yes, that will make your interval narrower. But if you want 95% confidence level and you sacrifice to do 90%, as long as you're able to accept that, then it's fine. But generally, if you are only comfortable to have a 95% confidence, if you require 95% confidence, it's not a good idea to lower the confidence level. How about standard deviation here? The standard deviation is really an estimate of the population standard deviation. And even though it changes from one sample to another sample, but the population standard deviation is behind of that. Eventually, the standard deviation, as we know, sample estimate is converging to the true standard deviation. So if the true standard deviation is large, we really cannot make the sample standard deviation to be small, very small. Okay, so the only thing that's reasonable and easy to change is the denominator, that's square root of n. So we change the n. Since n is in the denominator, square root of n in denominator. So if we increase the n, this ratio st over square root of n will become smaller, and correspondingly, the interval will become shorter. Okay, so the good way is to collect more data to make the sample size large. And as long as the sample size gets larger, then our interval will become shorter. So that's the solution. So how much does this n affect? We already saw that the square root of n is in the denominator. In other words, if we consider the width is okay, what is the width? So that's our interval, and here's the center, and the width let me redraw that one. So the entire width of the interval is from this point to another point, and total of that is really twice of the percentile times the sigma SD over square root of n, the standard deviation over square root of n. So the width is about this much, and W represented the width, okay? If W is the width, and I want the interval, so if I double my sample size, what happens? N here, if we change to 2n instead of a single sample size, a single n, then what will happen is that this interval, now the new width becomes this much. So compared to the before, if we look at the old width, this one is the old width, and here's the new width. The new width compared to the old width is going to be equal to the square root of n inverse, and here is the square root of 2n inverse, because the rest of the terms would all cancel out. And in the end, the ratio is, let's see, when we have a square root of 2n there, yeah, this new width would be shorter. Oh, I'm sorry. Yes, this is the 2n is on top, and the denominator is the old one that does not have the 2. So let me correct it here. So what I have is a square root of 2n in the numerator here, and then the ratio will become 1 over square root of 2. So that's, if you double the sample size, what happened is that the interval will decrease. The new interval is going to be just the old interval divided by the square root of 2 in terms of width. Now, if I want to shrink my confidence interval width by half, how should I change my sample size? So in this case, you really want the new interval's width to be the half of the old width. In this case, we are basically having, let's say, for the new interval, the ratio, we will have, again, that the 2, the z, and the SD, the square root of n new, this is the new interval's width. And similarly, the old interval's width will also have the SD and square root of the n old. And this ratio should be equal to this half. And let's cancel out everything common, and what's left is simply just the n old, oh, excuse me. So the new sample size here, and that takes the square root, and then we have the old sample size is square root inverse, that should be equal to half. So what we have in the end is so by the end, I'm going to put it over here. So n new is going to be equal to 4 times of the n old. So if we want the width of the confidence interval to shrink by half, then what we need is to change the sample size to be quadrupled. So basically, increase by n would correspond to a decrease of the width of the interval by square root of n. Okay, so you can also say the width of the interval is inversely proportional to the square root of n. How is the width affected by the sample size? We already saw that, and now we try to consider the sample size calculation if we have the width of the interval, desired width of the interval known. So to do that, first first we need to know what is the width of the interval that we want to consider. So basically, when you consider to construct the confidence interval, ahead of time in your mind, you want to have an idea of how wide you want the interval to be. And this width of the interval basically is your tolerance of the error because we are putting into the standard deviation into there. Okay, so this first part is to have an idea of desired width of the interval. Let's call that the W is the width of the interval. And the next one is decide the level of significance. For example, you can, if you set it to be 95% or 99%, etc., whatever that you're comfortable. So that's the desired level of confidence. Once we have those, next we would use this to determine what sample size is needed for the width, for the confidence interval to be of specified width. Because we already know from the previous slide that the width is really twice of this z sigma over g times standard deviation over square root of n. So we also need to have an idea about the standard deviation sigma. If sigma is known, we're going to use it. But if sigma is not known, we will need to come up with some sort of guess about it. Okay. So we can write the width equals so the twice of the z and sigma over square root of n. That's the width. Square root of n is equal to the width. So from here, we'll solve for this n. We can multiply square root of n on both sides. Once we multiply that, square root of n on both sides, we will have the 2z and sigma over the w, that becomes the square root of n. So we can square both sides. That will give us 4 times the z squared and sigma squared and over w squared. So this is the formula for the sample size n. Okay. If we are given the width w, our sample size calculation is 4 times of the squared of the z, the percentile from normal, and times the sigma squared over the w. Sometimes the question, instead of you giving you the width, it gives you a half of the width. When do they say half of the width? They say to estimate mu within E. To estimate mu within E. That's basically talking about that your interval is going to have here's the center, and the center on the both left side and right hand side. This part is E, and this part is also E. So basically, when the question, the statement says that I want to estimate the population mean within E, that's really saying that half of the interval width is the E. And this E is often referred as a margin of error. E is the margin of error. Okay. So if E is given rather than the W, we know the E and the W is twice of E. Therefore, the formula will change to the Z squared sigma squared over the E squared. What about the situation when sigma is not known? If that's the case, then we have to give some sort of estimate of the sigma. You know, here we are trying to consider to estimate the mu with a interval estimate. If we don't even know the mu, quite often we also do not know anything about the sigma. So using the sample standard deviation may not be reasonable. But if you do have some prior study that reported some standard deviation or estimate of that, then you can use it. Some other times you might be able to see the range of the data. If that's the case, we could also use the range to help come up with an estimate of the sigma. So how do we do that? This range, using range to estimate sigma, is only approximate in the sense that it relies on the distribution of the data in order to for this range to be valid. but still it's better than nothing. So that will, so let's proceed with the range to estimate the sigma. So generally, how do you use the range to estimate sigma? If the data are normally distributed, if data follows normal distribution, then earlier when we learned the empirical rule, we know that 3 standard deviations will capture all of the data. And so mu minus 3 sigma, mu plus sigma, 3 sigma captures 99.7% of data. And if we consider the mu minus 2 sigma and mu plus 2 sigma, so plus or minus 2 standard deviation, that captures 95% of the data. And this 95%, you know, is like when we try to consider the observed data, how much chance that the data would be outside of the 95%. Of course, it's 5%. Or if we consider 3 standard deviations, that's 0.03%. So this one is 95.4%, okay? So if you know that the range, definitely you want all of the data to be within a certain number. So the range, for example, all of the data is between, for example, 10 to 20. In that case, you are really specifying that from 10 to 20, this spread of 10 is 6 standard deviations. But if you do not want to be so conservative, instead you think that what you saw is in the majority of cases rather than in the all of the data. So in that case, you can use the 2 standard deviation on each side to consider this range. In other words, if you have observed some of the data in the past, and this is some of the data, you can think of it as if that's just the majority of the case, which is within the 95% situation. And therefore, you use the 2 standard deviation below and 2 standard deviation above to consider the range. In that case, the lower upper bound together gives only the 4 standard deviations, and use that to compute the standard deviation. Okay, so if you have a range, and this is talking about you want, you know that almost all data are in this range. This range, I'm going to write it as low and high, a low L and B, okay, in this range. In that case, you can estimate the sigma, with this B minus L divided by 4, because we roughly think that the 4 standard deviations, that's around 95.5%. That's because here we are talking about almost all, okay? We are considering the 95% as if that's in reality most of the time what we already would observe. So just a quarter of the range will give us estimate of the standard deviation. Here's an example. Decide the number of serial cartoons to sample. A federal agency decided to investigate the advertised weight printed on cartoons of a certain brand of cereal, and the company in question periodically samples the cartoons coming off the production line to check their weight. From the company, it says that a summary of 1,500 of those cartoons become available to the agent, and they say that the mean weight is 11.8 and the standard deviation is 0.75. Use this information to determine the number of serial cartoons the federal agency must examine to estimate the average weight of cartons being produced. So basically, the company declares their average weight and also their standard deviation. And here the federal agency just want to check it. And the federal agency will not take the words of the factory directly. Instead, they need to do an estimate of the mean based on their own sample. And the sample, before taking the sample, the federal agency need to decide a sample size. So here is the question is asking about what sample size the federal agency should examine in order to get a confidence interval of with 0.5 and 99% confidence level. So here 99% confidence level. So we are looking at we need to use, recall, the sample size formula is the 4 times the z square and the sigma square and divided by the width square. So in this case, the z comes from the 99%. So we'll use the z of 0.995 in the computation. This z 0.995 can be obtained by the Q norm. We put in 0.995 there. And then for the sigma, in this case, we have standard deviation 0.75, so we're just going to use it. Z is that, okay. So sigma will use 0.75 and the W will use 0.5. And once we finish computation, we'll know the sample size. Quite often, the computed sample size is going to be in a decimal point. We would always round up to give the sample size. Like this one here, the width is 0.5, and here is using the half of the width, the margin of error E. Margin of error E is 0.25, and we put in this one, 2.58, is the percentile, 99.5 percentile. After the computation, we see 59.7, then the conclusion is that the federal agency need to obtain a sample of 60 in order to get the confidence interval width of 0.5 at 99% level. So here, this 59.7, we would always round up. Even if this is 59.1, you still need to use 60 because this sample size, whatever that's resulted, is the minimum that's needed to achieve that level with that width. So if you suppose you computed this one and what you get is 59.1, and if you're going to use 59, then the width will be wider than the desired 0.5. Okay, so if you compute the whole thing in R, first write the Z is the Q norm, and then the sigma and the E, and then you put the formula in there. That'll give it the sample size computation. Okay, so that's the sample size example. The next one here, we want to consider the cost of textbooks, and this need to be estimated. And in order for these estimate to be useful here, they want the width of, so they should be, this question states that the estimate should be within $25 of the mean. So this is talking about the margin of error is 25. So the estimate should be within $25 of the mean. So this is saying the margin of error is 25. Okay. So from data collected in previous years, the university officials determined that the annual expenditure for textbooks has histogram that's normal, with the cost ranging from $250 to $750. So this basically, this is from the past data. One is from the past data and it's normal and giving the range, then we can estimate the sigma. The sigma, because it's past data, we would believe that these data are within those 95% of those range. So we use the 4 standard deviations of this range to, the range give us 4 standard deviations. 1050 minus 250, that give us the estimate of the standard deviation. So 125, okay. And once we have this sigma estimate, then we can give the sample size calculation. So range is estimated, the standard deviation is estimated to be 125, and then the margin of error is 25, and the level of confidence 0.95 give us the z to be 1.96. And then the computation for sample size is the z square times the sigma square and over the e square. And that gives us 96.04. Again, if it's slightly over 96, then we need to round up to 97. So the sample size needed is 97 in order to estimate the cost of the textbook within margin of error of $25 at 95% level. So summarize what we learned in this lesson is that we considered the confidence interval for the proportion. Maybe here it's good that I'm trying to write down. The CIX confidence interval calculation for one population mean. Okay. So for mu, when the sample size n is large, with the large sample size, in that case, our confidence interval is computed by the x bar plus minus the z percentile, the normal percentile, and then the standard deviation over square root of n. And this can be computed in R with the Q norm. The Q norm command. Q norm gives us percentiles. And this Q norm command, we just need to give the two of the percentiles. One is the alpha over 2% like proportion. The other one is 1 minus alpha over 2 proportion. And then afterward, we specify the mean, which is the x bar. And the standard deviation is this ST over the square root of the n. So this is the center of the confidence interval, and this is the standard error of confidence interval, and this will give us the two of those percentiles. Okay, so that's the confidence interval computation. And for proportions, if we have large n, with the large n, the confidence interval for proportion can be computed as the sample proportion plus minus the percentile from the normal, and then multiply the standard error, which is the p hat 1 minus p hat over n. Generally, this n need to be very large. So if p is not very close to 0.5, p not close to 0.5, we will need this n to be like over 1,000 or even more, okay? And for the interpretation of the confidence interval, this is if the data collects, if the experiment is repeated a large number of times, if the experiment is repeated a large number of times, and data were collected each time, a confidence interval is calculated for each of the data set. Each data set. Then overall, around 1 minus alpha times 100% of the CIs contain the true mu. So that's the interpretation of confidence interval. It's always based on the large number of confidence intervals constructed in the same procedure from different data. And the sample size computation, if you're given the W is the width W, and the sample size will be given as n equals 4 times the z square, and then the sigma square over the W square. So that's if you are given the width of the interval. On the other hand, if you were given the margin of error, so if E is given, margin of error is given, then it's simply just the z square, sigma square, and then divided by the E square. Okay, so that's this summary of what we learned about this confidence interval part.